In this chapter 5, we look at magnetostatics, and we exactly start with an example of a battery. But before we get into the battery, I want to show something that the book is trying to prove. So, for example, if we have two wires parallel to each other, what happens with the wires? Do they attract each other? Do they just repulse each other? Well, actually, nothing happens. Just two wires. But if you attach a battery to the wires, oops, that's not what I meant to do. Okay. Okay. Plus and minus here, and then of course these two cables are touched on the other side. What happens to these cables? Well, the two cables repel each other, and they actually end up having this shape right here. So the blue is what happens after the battery is attached. Why does this happen? Well, the current is flowing this direction, first of all, and it's fine. And the two cables attract each other, repulse each other. So your first thought might be, well, that's because the two cables have electrons inside of them, and the electrons, of course, repel each other because on on opposite sides. And that is incorrect. That is proven because, for example, if we just hold two wires next to each other, these two wires have electrons out of it, and nothing happens to them. The only thing that the battery does is make the electrons flow inside the battery. So, for example, here, there's no moving electrons on either side, and they're not attracted to each other. So the point is that the electric field is not what makes these two wires attract or deflect each other. In fact, if we, for example, were to put a battery in another example, like you can see on the figure 5.2, the second example, if we have two wires with the current going in the same direction somehow, well, actually, and this was hooked up to the battery, minus plus, and then with plus over here, okay, they actually attract each other, but there are always electrons out of it. How does this happen? Well, this happens because another force is added to this system. In this case, the force is the so-called force B, magnetic force. Well, why is it called B? Well, the reason is actually irrelevant to why it's called B, so I'm just going to go and ignore it. But just so you're aware, every time you see B on any physics-related argument or paper, you know that it's talking about a magnetic field. Now, this is a field like the electric field. And how does this act? Well, if we have, for example, a wire with electrons flowing up, for example, the magnetic field will point this way. Well, actually, it just turns around. Let me just make it clear. It goes around the wire, and that's how it points. For example, to make it clear, if you were to put your thumb pointing up like the current, so the thumb points up towards where the current goes, towards where the electrons are going, towards where the current is going, you will have the other four fingers curling around the bottom of the thumb, for example, and you would see that the magnetic field is pointing exactly in that direction. Now, a good picture is the one that you can see in the book, and that I think explains it better than actually talking about it. And of course, if the electrons or the current was flowing the other way, so pointing down, our magnetic field will be pointing this way. Now, one thing is that it points this way everywhere along the circle. So something like this, to be more exact. Oops. And that is the solution to, the explanation of 5.11.